Okay, these are some problems from section 5.5, and this is number 63, and these are equations, trigonometric equations that we're solving on this interval from 0 to 2 pi. So I've kind of worked it out, save a little bit of time. And then we'll take a look at these. So we've got 2 cosine squared sine plus the sine of x minus 1 equals 0. So first of all, I notice that I've got some cosines and some sines, so I can try to get them all in the same function. So what I'll do is I'll rewrite the cosine. I'll use the Pythagorean identities. The sine squared plus the cosine squared equals 1. So the cosine equals 1 minus the sine squared. So I'll make that substitution. So we're using this trigonometric identity. Instead of writing this, I'll write this. Then I'll multiply out. So I've got 2 times 1 is 2. 2 times sine squared of x plus sine of x minus 1 equals 0. And then I'll just 2 minus 1 is 1. So I've got negative 2 sine squared of x plus the sine of x plus 1 equals 0. Then I'll get rid of this leading minus sign. I'll divide everything by negative 1, so that makes this positive. Negative, negative, equals that. So now I have a trinomial in sine of x, so I'm going to use the z substitution. It's a little easier to explain that way. So I'll let z be sine of x, and if z is sine of x, z squared is sine squared of x. So I can rewrite this as this. Hope that makes sense. And I can analyze my sines. If I look over here, and this is kind of what we call a general trinomial, but it's an easier general trinomial. The only way I can get 2z squared is 2z times z, and the only way I can get 1 is 1. I just have to analyze the signs. I know the signs are going to be different, and I'm going to end up with a negative sign, so I've got to figure how this is going to work. I'm going to multiply this term times this term, so that's going to be the bigger one. So I'll make that the negative. And then I'm going to make this the positive. And again, you always check it. So we can always check that. So that's 2z squared. And this is negative 2z plus 1z is negative 1z and negative 1, so that checks. Right? And then if I set each of these equal to 0, I've got 2z plus 1 equals 0. So that means that z, if I subtract 1 divided by 2, z equals negative 1/2. If I add 1 to both sides, z equals 1. And then I go back and I resubstitute. Z is just the sine of x, so the sine of x equals negative 1/2, or the sine of x equals 1. I know the sine equals negative 1/2. I know the sine of x equals 1/2 at pi over 6, so it's negative 1/2 in the second and third quadrant. I'm sorry, third and fourth quadrant. So that's 7 pi over 6 and 11 pi over 6. And the sine of x equals 1 just at pi over 2. So those are your answers. Okay? So this might be a little bit fast, so you can always pause it, look at it, rewind it a little bit, but maybe it won't be so long to download. Okay? Okay, number 65. Okay, the same idea. We got the sine squared of x minus 2 cosine of x negative 2. Again, I've got cosines and sines. Now the cosine is in the linear term. The sine squared I can change by using the Pythagorean identity. This is the same thing as 1 minus the cosine squared of x. Again, minus this. I'll simplify it. I kind of did this in one step to save steps because it's just a leading 1. So what's 1 negative 2? That's negative 1. So I've got negative cosine of x, negative 2, cosine of x, negative 1. And then again, I divided by a negative sign, so I made this positive, made that positive, made that positive. And again, I'll use the z substitution. So instead of sine, this time I'm going to let z be the cosine. So z equals the cosine of x, z squared equals cosine squared of x. So this now looks like this. And that's just a nice trinomial square. As we can see that this is a perfect square, the square root is z. And this is a perfect square. The square root is 1. And we do have twice the product in the middle, so there we go. So I got z plus 1 squared equals 0. So if I take the square root of both sides, z plus 1 equals 0. So z equals negative 1. So the cosine of x equals negative 1. And that's only equal to pi on that interval from 0 to 2 pi. Should have wrote that down at the beginning too, because again, the interval is very important. If it's open, then it causes a lot more trouble. So that's our domain. That's important. Okay. And then 67, the same thing. We have the same interval issue going on here. 0 to 2 pi, open to 2 pi. All right. And this is what we've got. There we go. Okay, 4 cosine squared of x minus 5 equals 5 minus 4 sine of x. So I put this on the right, left, and this. So I added 4 sine of x, and I added 5 to both sides. And then again, the same thing. I've got a linear sine of x, but a square cosine, so I can change this to sine, so this all matches up. So 1 minus the sine squared of x, 4 times that. These are the same. Then I can remove a parentheses. 4 times 1 is 4. 4 times negative sine squared of x is negative 4 sine squared of x, and then I've got these the same. Okay. And then what's 4 minus 5? That's negative 1. That's what I did in this next step over here. And then I can divide everything by negative. So I make that positive, make that negative, make that positive. And then again, I'll use the z substitution. And let z equal sine of x, so z squared equals sine squared of x. So I can rewrite this as 4z squared minus 4z plus 1. I started to think of this as a general trinomial, so I started working, and then I just noticed, well, this is actually a trinomial square. This is a perfect square, that's a perfect square, so this is going to end up being just 2z minus 1 squared. Then I can take the square root of both sides, so I end up with 2z minus 1 equals 0. And if I add 1, divide by 2, z equals 1/2, and that implies that the sine of x equals 1/2. And the sine of x equals 1/2 at pi over 6 and 5 pi over 6. It's positive in the first and the second quadrant. Okay, let's take a look at number 69, the next one. So the sine of 2x equals the cosine of x. Now I'm going to use the two-angle formula because I want only one x, not two x's. This is all mixed up. So I'll change this to 2 sine of x cosine of x. This is our two-angle formula. And we'll derive that before using sine, cosine, cosine, sine. Okay, so this is the two-angle formula. Sine of 2x equals 2 sine of x cosine of x. Again, that's easy enough to derive. And then once we have it like this, we can pull this out. Again, I got to show you how to derive that if you forgot, so just so you can see that. We can think of this as the 2x is the same thing as the sine of x plus x, right? And that, we know that that equals sine cosine, same SIGN, plus cosine sine of x. But these are the same. I've got sine of x, cosine of x, and this is just the same thing as the sine of x, cosine of x, so I've got two of those. So 2 sine x, cosine x, and this is just x plus x, so that's just the sine of 2x. So you can see how easy that is to derive. It's very easy to derive. Okay, real easy to derive in case you forget it. So this is what we use here. And then now I can factor out a cosine. So we factor out the cosine, and what's left is 2 sine x minus 1. And then I've got two things that multiply to give 0. I know one or the other must be 0. So I set them each equal to 0. The cosine of x equals 0, or 2 sine of x minus 1 equals 0. Well, the cosine of x equals 0 at pi over 2 or 3 pi over 2. And you can look at your cosine graph. Okay. Or the sine of x equals 1/2, and that's going to be at pi over 6 or 5 pi over 6. Like our last problem in 67, we have the same thing. It's positive in the first and sine is positive in the first and second quadrant. So that's all you have to do with 69. Okay, I hope that makes sense. And again, if these are going fast, just pause and take a look at these and make sure you get them. Okay, hope those help.